All right. This is the last section, charges on nested conductors. And this is going to be about where you have something called a nested conductor, which is where you have a shell maybe around another conductor. And so it's nested within the shell, right? Consider a sphere of radius r and spherical shell of inner radius 2r and outer radius 3r. The sphere carries a net charge positive q, and the spherical shell carries a net charge positive big Q. What is the net charge enclosed by a Gaussian sphere for each of the following radii? So if we have half of r, that means that we are inside of the inner sphere. And so we're in the bulk of a conductor, so we'd say 0, because we're in bulk of conductor. Okay? It says bulk. Okay? R is equal to 1.5 R, so that's going to be right in like the middle kind of the two conductors. Okay? The enclosed charge of something out here is going to just be the positive Q that's on the inside cylinder. Just inside cylinder. Okay? 2.5 R is going to be between 2 and 3, which is actually going to be, again, in the middle of a conductor. So 0 bulk of conductor. Okay? And then the last one is going to be if you're outside of the conductor, and that's going to be the total enclosed charge, Q plus big Q, total of both cylinders. Okay? Now, based on that information, okay, the charge on each of the following surfaces. So the first surface is going to be the surface of the inner cylinder. The inner cylinder is going to have a charge of positive Q. Okay. Because the outfacing surface, so the outfacing surface charge, okay, equals the all net charge enclosed by that outfacing surface. Okay. If you're looking at the inner, this is the inside of the shell, okay, the inside of the second cylinder, or the shell, okay. On the inside surface of that, we're actually going to have so these positive charges on the inner shell are actually going to hold equal and opposite sign charges on the inner surface of that outer shell. So we would say for 2R, okay, we would say that this is going to be negative Q because the in-facing surface has exact opposite charge of the surface it faces. Okay? So it's going to have the exact opposite. So same number of charges, opposite sign. Okay? And then 3R, same thing, is going to be Q plus little q, because again, outfacing, same reason as this right here. Okay? That's the same reasoning. Okay? The last example is going to be a example in where how can we find so each of these little lines, this is a shell, okay? So there's a bunch of shells concentric to the sphere, and there's 9 surfaces. So there's the outer surface of the sphere, and then each of these 4 have inner and outer surfaces, inner, outer, inner, outer, inner, outer, right? So we can figure out the charge on each one. Remember, it's easiest to start from the center, okay? This is going to have positive 5Q on it, because that's what what we've said earlier, right? Outfacing surface charge is all net charge enclosed by that surface. And then as we move to negative 2, okay, we should see on the inner surface it needs to have the exact opposite. So it's going to have negative 5Q. In order for this to be true, the outfacing surface needs to have needs to be the net charge enclosed by that surface. So this is going to be, in order to get this to be satisfied, we would need to have this be equal to positive 3q. Okay. And then the negative 4q, this is going to have a negative 3q right here. And then to get this to be satisfied, we need to have a negative 1q on the outside surface. So then that's going to pull positive 1q right here, and then the outside needs to have a positive 2q. Then you'll have a negative 2q here, and then you should see that at the end here you have to have a positive q. Okay? See how that kind of works out? It's kind of weird, but that's kind of how concentric shells work out, right? And nested conductors, really. Okay? All right. That's it for Unit 8. I did 36 pages, and I did it all in the span of a couple hours, which is crazy. I want to go to sleep now. Okay.